This is worked example 2 from page 12 of the LO3 course notes for statics. In this worked example, we're going to use Bose notation to complete the nodal analysis of each of the 4 members in this diagram. And those members are AB, BC, CD, and DD. Important to note that there's not a member at AD. These are just 2 points that join our structure to the support wall. We're only interested in the members joining the other points. So before we begin and start to use our method of Bose notation, it's important to observe a few things on the diagram. Firstly, that the lettering corresponds to the nodes, not the spaces between the forces. So A, B, C, and D are the nodes. The spaces are actually not the same, and we're going to have to label these separately. So we're going to choose the labels P, Q, R, and S for our spaces. And we'll try to avoid confusion here, but when it means we're working to the notation, we will have things like vector RS representing member CD. So I'll try to link back each time, but sometimes having different letters here is going to make things a little bit confusing, but we'll do our best in order to try and keep this nice and clear. The other thing to observe is that we've been given some of the angles, but it might be nice to have some of the other angles in the question. There's 2 angles we can give ourselves straight away. These are both right angled triangles that we've labelled the spaces Q and R. So we can say that the other angle in each triangle must be 60 degrees to add up to 180. This allows us to do something else as well. If we take a horizontal line out from point D, we know that between the wall and this line we must have 90 degrees. And since there's 2 30-degree angles already, this means this must be a third 30-degree angle. If we were to complete this horizontal line and draw a vertical line down from the applied force here of 10 kilonewtons, we can see that this too is a right angled triangle, which would have an angle of 60 degrees here. And if we took that vertical line up this way, from above the force, we can see that we have 2 60-degree angles and a missing angle to make up half a circle, so that 60 degrees would have to be here as well. Now we might not need all of these angles solving this question, but it's helpful to have them to hand when it comes to drawing our scale diagrams. So having somewhat annotated the diagram for the question, we're going to begin our node analysis, and we're going to start at node C, because that's a node at which we have a force already being applied. So let's draw a space diagram representing node C. What we have at this node is we have a 10 kilonewton force acting down the way and out from the node, and in or out of the node, but certainly joined to the node, we have a force due to the member BC and a force due to the member CD. We're not going to use the letterings of B, C, and D here because they don't correspond to the spaces. The spaces are in fact R, S, and P. And we need to use this here in order to keep ourselves right so that we're going to be able to use Bose notation correctly. This means that each of these vectors can be labelled in accordance to P, R, and S. So the 10 kilonewton force that we have already is the force vector PS. The member CD is going to be represented by the vector SR, and the member BC is going to be represented by the vector RP. So we've labelled all of our vectors in accordance with the steps required for Bose notation. Having labelled our spaces and labelled our vectors, we can now proceed to drawing our diagram. Remember, it's a scale diagram, so it's important we establish a scale before we begin drawing. And what we're going to say here is that 1 centimetre is going to correspond to 1 kilonewton. On your piece of paper, you may be able to get 2 centimetre to 1 kilonewton scale, but it might be harder to do anything greater than that. Following the instructions, we're going to start off by drawing a cross here on our paper just to have a starting point. So let's take our cross here on our page, just to give us enough room to draw all of these different forces in. And the first thing we can do is to draw in our vector PS, which is going to be acting down the way. And because we made our scale 1 centimetre to 1 kilonewton, a 10 kilonewton downward force must be represented by a 10 centimetre downward line. So we'll draw this in just now. That's 10 of the short divisions on this ruler, which we're calling centimetres to correspond to what you would drawing. So we'll follow the rest of the steps in the notation, which is the way we'll put an arrow indicating its direction, and we'll label one end P and one end S. And the reason for doing this is that we know which vector to connect to each end of it. We'll be connecting RP to the top and SR to the bottom. And where those two vectors cross is going to give us a point R, and from that we'll be able to derive the direction, and therefore the nature of the members and also their magnitude. So the next step is therefore to connect vector SR to the point S. What we know about vector SR, and we can add this into our space diagram from our initial diagram, is that this line acts at 30 degrees from the horizontal. So we can have a horizontal line drawn at point S and mark up 30 degrees from it to find the direction of vector SR. The dotted line here indicates a horizontal line, and then I'll measure in using this ruler, but you could use your protractor. And we want to draw a line touching point S, and because we don't yet know the direction where it's going to be acting towards or away from the node, we draw the line in both directions connected to point S here. We now need to join the vector RP at point P. Well, again, looking back at our diagram, we can get a bit of a guide for what angle to draw this at by observing that this vector is 60 degrees measured round from the vertical line, and the vertical line is just an extension of the vector PS. So we can draw a little dashed line up from that. I'll measure around 60 degrees from there. So although it says 30 in my ruler, it's because I've measured 60 away from 90. And we'll draw a line through the end of this vector here. You can see we've left our green line slightly short, and that might happen when you draw this, and don't worry about it. Just line your ruler back up with your original vector you drew, so like this, and then extend it a little bit further so that the two lines cross, because this point, I'll change my pen back to green, this point where the two vectors cross, that is where point R is. We can mark that in our diagram as well. And so we now know what we need to measure in order to find the magnitude of each vector. Before we do that, however, though, we can indicate the direction in which each force is acting. We're going to have a circuit starting from coming down our vector PS, which means we go up to the right in the vector SR, and then up to the left on the vector RP. And we can indicate this on our space diagram as well. So going back here, we can see this is going to be acting away from the node. This is going to be acting towards the node. And what does this tell us? Well, it tells us that in the case of the vector Rp, that this member is under tension. And because it's under tension, this means that it's a tie. So what we can say, we'll just create a quick table here just now. Well, we know that this vector, this blue line, represents member BC. Because the arrowhead is pointing away from the node, we know that the beam is under tension, and that tells us that it's a tie. So we can label BC as a tie in our little table here, determine the nature of that. Our vector SR corresponds to the member CD. Here we have the arrowhead acting towards the node, and this means that the member must be under compression, and a member under compression is a strut. So CD is a strut because that arrowhead is pointing towards the node. So we've learned something about both of them already. The next thing we can do is we can find the magnitude of each of these members as well by measuring the corresponding vector we've drawn. So measuring the vector SR will tell us the magnitude of the internal force within CD. Now, it's quite hard for me to measure accurately off the whiteboard. It looks like it's about 10 kilonewtons from here. So rather than rely on this, I'm going to go with the answers, which I'm sure you'll obtain in measuring more accurately with your ruler. So if you had done a 1 centimetre to 1 kilonewton scale, you should be measuring a line of around about 9.8 centimetres, which would tell you that the strut has a magnitude, the CD strut has a magnitude of 9.8 kilonewtons. And I could see it was about 10 on my measurements. It's an indication that we've done things roughly right here, but simply not enough accuracy to be certain from this diagram. And measuring this line here, again, this looks like it's about 10 centimetres as well, maybe slightly less. And of course, going back to the answers in the course notes, it is slightly less than 10. So if you're measuring this on a 1 centimetre to 1 kilonewton scale, it'd be 9.9 centimetres, indicating we have 9.9 kilonewtons. And it makes sense to go with the answers from the notes here because we just cannot get the same level of accuracy, even though we can demonstrate the method on the whiteboard. So this is good and helpful because it gives us a force acting at node B, and that's enough for us to find out the other two forces because members AB and BD connect to node B, and we have the information about the forces acting in member BC. So we can select node B, and from that we're able to solve the rest of the question. And the only other node we could have considered would have been node D, because that's the only other node we have any information about from knowing what's happening in CD. But had we selected that, we would have to do 2 more pieces of work in order to find the complete solution. So let's look at node B next. Well, node B, we have 3 members interacting together. We have the member AB, the member BD, and the member BC. We're going to start labeling these in a second, but we can actually say something about the member BC. We know that it was acting away from node C, And because internal forces are indicating that we have the internal forces acting in the way, that means that at point B, it will also be acting away from the node. So we have a force here acting away from the node, and we know the size of that force as well, because it's a balanced force, so it's going to be the same force that was acting away from node C, and so that's a 9.9 kilonewton force here. We also have labels for our spaces. This is going to be space P here, space Q, and space R. Other thing we know is the angles between these members as well. So we're going to label this carefully, accurately. This is going to be a 60-degree force. We should have made it clear that that top line there is a horizontal line. Maybe redraw it a little bit better. This line, that looks pretty good. It's horizontal. And this angle here is 90 degrees as well. And that means that we can also say this angle must be 30 degrees below the horizontal. Remember, those three angles need to add up to 180. So this gives us, I think, enough information to be going on in order to begin this question. And also, the last thing we should do is label all of our vectors as well. So we'll label this vector PR, this vector RQ, and this vector QP. And again, this labeling is done so that we know we're going to join RQ to one end of PR and QP to the other end for the scale diagram that we now draw. So we'll do what we've done before. We'll draw a cross here. And we'll start off with the force we know. We know we have to measure down an angle of 30 degrees from the horizontal. So even though I can do this automatically with this ruler, if I do this with a protractor, I would draw in a dotted line and I'd measure around 30 degrees from here. And then I'd measure a line of 9.9 centimeters. I'll do my best to make an approximation for this here. This looks just shy of the 10 mark there. It'll certainly be good enough to illustrate the solution. And we'll indicate again this is acting in this direction with 9.9 kilonewtons, and it represents the line PR. To the end of this line, we're going to join the vector RQ. Now, what we know about RQ is it acts at an angle of 60 degrees below the horizontal line. You can take that from the question. So we're going to draw a dotted line here. And measure around 60 degrees from this. And although we don't know if this is pointing towards or away from the node yet, we know it must be pointing in one of these two directions, running through this point in this direction. We can draw our green line. I'll make it nice and long so we try and avoid the mistake we made last time. And this will be far enough, and you'll see why in a second. So we also have to draw a horizontal line running through the point P, which represents the vector QP. So if we put our ruler back on the page, and draw a horizontal line running through P, blue for this time, we can see clearly where these two intersect and what must be the point Q, where the green and blue lines intersect. And again, following round the arrows If we follow the red arrow down to the green line, the green arrow must point up to the blue line, and the blue line must point back towards the red line. So we can use this to indicate the direction of our forces on the space diagram here, which means that we have QP heading away from the node, indicating it's a tie, and we have RQ heading towards the node, indicating that it's a strut. And so we remember from our diagram that QP corresponds to AB, so AB is a tie, and that our other vector, which is heading towards the node, RQ, corresponds to BD, meaning that this is a strut. So all that remains is to measure the magnitude of each of these vectors and convert it back into kilonewtons. So measuring my vector QP here, it's 11 and a bit, somewhere between 11 and 11 and a half on my diagram. Now, this corresponds not too badly to the correct answer, which for AB is 11.2 kilonewtons. And I'll measure my vector RQ, which corresponds to the member BD. And this goes 2, 4, 5, so somewhere between 5.5 and 6 centimeters in my ruler. And again, a pretty good comparison because the answer here is 5.7 kilonewtons. So if you're drawn a 1 centimeter to 1 kilonewton scale, you should be measuring 5.7 centimeters off your ruler, which you convert back into kilonewtons. And that completes worked example 2. So in each case, we drew the space diagram, drew our scale diagram following the steps for Bohr's notation, did that for node B as well, should label that node B there, and it enabled us to find the direction of the internal forces, telling us if it was a tie or a strut. And then because we've drawn it to scale and measure our angles accurately, we're able to find the magnitude of these forces as well. And it's summarized here in our table.